This is, I think, my favorite physics topic ever. I am a vocalist by training, so I absolutely love the physics of sound. I've been a musician since I was in the fourth grade, um, and this is one of my favorite things to teach. Um, Take a look. I did post some bonus content in the Canvas page. It is a link to a video that came out earlier this year about the physics of consonance and dissonance and why certain chords sound really nice and certain chords don't sound really nice to our ears, and how that depends on the instrument as well as the frequencies. It's a really cool video. Highly, highly recommend. Minute Physics is awesome. We're going to be looking at the kind of base ideas that that video builds on. And that is these fundamental frequencies and these higher harmonics and the standing waves that make them happen. So we're given this fundamental frequency is 82.4 hertz. And our job is going to be to find the speed of the wave on that string and what tension is needed. So we want V wave and tension. Well, we know where tension shows up in this equation here. However, we first need to find that V. So do you guys remember what the basic, nope, not going to use that word. Do you guys remember what the fundamental equation is when we're talking about waves?
Is it the wavelength one?
Probably. Can you say more
The
about that?
wavelength equals 2 times the length.
Almost. So that's going to be really helpful when we're thinking about how long the string is and that sort of thing. Um, the one I'm thinking of is that the speed of a wave is always denoted by these two things.
Oh, is it speed of wave equals the frequency times the wavelength?
Yes. My initial question was very vague, so my apologies. But this is always the equation that we come back to when we're thinking about waves, because every wave has a frequency and it has a wavelength. This is true of sound waves, of waves in strings. This is also true of light waves, as you guys will see if you take general physics 2. And this part is going to rely on the assumption that the speed of this wave in the string is constant. So we know what the speed of the wave is in this string from part A. And so we can say that different harmonics have different wavelengths. So once we reason through what those different wavelengths are for the different harmonics, then we can plug those in with the velocity we found in part A to get these F2 and F3 frequencies. Finally, in part C, oh my goodness. Finally, in part C, we are putting our guitar now near an organ pipe that's closed at one end, and we see it excites some sympathetic oscillations. You might already know a little bit about sympathetic oscillations from the pop culture, I guess, image of an opera singer holding a wine glass. This is my crazy cat lady glass that I use for this demo. You sometimes see an opera singer holds the glass just by her face and sings this beautiful high resonant note, and the glass just shatters. That is possible. Maybe not with something this thick, but you can excite sympathetic oscillations in something like a glass using just your voice or using another instrument. And that's what's happening in this pipe as well. So we are asked to find the length of the pipe, given that the temperature, which I'm calling TC for this problem to match the notation in the equation that was given to us, is 10 degrees Celsius. Today's lab is looking at oscillations. So you guys have a spring in your lab kit. Your spring probably comes kind of stuck together like this, and you'll have to pop all of those coils off of each other, which is relatively easy to do. So don't worry too much about breaking it. When I demo this, I'm going to demo it with about half the spring because I don't have 4 meters of space to show you guys. But when you do this, you'll stretch out your spring to roughly 4 meters. If you can't get it all the way to 4 meters, that's fine. You just want to have a good amount of stretch in your spring because that's going to make it a whole lot easier to see the waves in your spring. So part A wants us to look at just the speed of a wave on this spring. So you will either pull back on your spring and send a pulse down the spring. And you'll notice that you get a lot of vertical motion with this as well. So if you find it easier and you have like a like door stopper near the floor that you can attach this to, it's much easier to see these oscillations in this horizontal direction if you don't have your spring in the air. So I recommend doing that if you find it really difficult to do this pulse just in the air. I definitely do. So just send a pulse down and back. You may want to time how long it takes for this pulse to go down and back a few times, because that's going to reduce the amount of error that you get. And from those measurements, find the speed of the wave. You'll time 10 complete up and down vibrations. So that's the time it takes for the antinode to go from the top to the bottom, back to the top. So make sure you're not measuring half periods. You want 10 full periods of this oscillation. And then from that, find the speed of this standing wave. Then in part B, we're going to do basically the same thing. You want to set up that standing wave with one antinode, record the frequency by measuring that period for 10 vibrations. There's a table in the lab setup, so feel free to recreate that table or copy paste it into your own lab report and fill it out. And then you will repeat this for 2, 3, and 4 antinodes. Getting 2, 3, and 4 antinodes is quite difficult if you don't have another person on the other end of the spring. And honestly, I think that this is one of the most fun labs to do with people. It always in the in-person class devolves into giggling and shouting, and it's a lot of fun. So feel free to enlist family members, enlist siblings, enlist roommates to do this. You'll find it's a whole lot easier to get those antinodes if you have another person at the other end.
I think we're just worried about the timing part of it.
For the lab.
Uh-huh.
So
Yeah.
essentially, like, I feel like this one is gonna garner a lot of human error just because of like stopping the timer at exactly when the wavelength like hit. So are y'all kind of prepared for there to be a lot of human error, or do you find that there shouldn't be? Like, it should be okay?
It's gonna depend on how many oscillations you time. So if you remember last week when we were doing the pendulum lab, we had you guys record 5 full oscillations so that you could
Yes.
cut down on that human error. So if you're measuring a whole bunch of oscillations, you can cut down on some of that error just because your total time is so much bigger than the error that you'll have, your error bars.